Hi, everybody. Welcome back to Dave's Math channel. I'm your host, David Tear, and this is my continuing feature on the Math Lovers book. And I'm starting a new section now. This is section 4.4. I'm still talking about complex numbers, but now I'm done with basic complex arithmetic. This is actually more complex arithmetic, but this is a very important and famous formula involving exponentiating complex numbers known as Euler's formula. So anyway, let's begin. So, what is Euler's formula? Well, I think Euler's formula is one of the most amazing things I've ever seen in math, and a lot of people agree with me on this. I think Richard Feynman even said he thought this was the greatest formula in all of mathematics. So what does the formula say? I'm not going to derive this formula, but what the formula says is a formula for exponentiating complex numbers. So you might wonder, I wondered this question myself before I even saw this formula. I remember when I was first learning about complex numbers and complex arithmetic in high school. I think it was either my junior or senior year of high school. I asked my teacher, I said, how do you exponentiate complex number? I said, is there such a thing as 2 to the I-th power, and what is it? And he said, yeah, there is. He said there is a formula for things like 2 to the I-th power, but it was beyond the scope of what we were learning, you know. And I remember when I was in college, I was in the library one day, in the engineering library, and I opened up a book on an engineering book on math, and it happened to have Euler's formula in it. And I was just blown away. I mean, this is one of the most amazing things I ever seen in my life. I just remember when I saw this formula. And I wrote it down in the middle of this slide. It says e to the I theta is equal to cosine theta plus I sine theta, where theta is supposed to be an arbitrary, it can even be a complex number, but it's easier to think of it as a real number. So think of theta as an angle. You're supposed to think of theta as an angle measured in radians. The units are important here. The natural measure of angle is radians. And they say a picture's worth 1,000 words, so I might as well cut to the chase and show you a picture here. And I actually have another video on Euler's formula, which I highly recommend you guys watch. I go into it in more detail than I do in this video or in my book. But I still thought I'd show you guys this picture. So here's what's going on. This circle on this picture is what's called the unit circle in the complex plane. It's just the circle of all complex numbers whose absolute value is equal to 1. If you like x squared plus y squared equals 1, where x is the real part of z. Remember we write z equals x plus iy. So this is just the set of all complex numbers z equals x plus iy, such that x squared plus y squared equals 1. Another way to say that is just a set of all complex numbers whose absolute value is equal to 1, or whose norm is equal to 1, if you like, because norm is the square of the absolute value. Like I said, I just showed you Euler's formula, e to the I theta equals cosine theta plus I sine theta. And it's pretty clear that if you pick any point on this unit circle, it's parameterized by this angle theta. The x coordinate, you probably learned this when you were learning trig. The x component is just cosine theta, and the y component is sine theta. And so I think you guys learned this when you were learning about the unit circle, when you were learning, sine and cosine as circular functions rather than trigonometric functions. You can think of them either way. I prefer to think of them as circular functions. So that means, this is how you learn what cosines and sines are. But what's remarkable about this is obviously this point on this picture is cosine theta plus I sine theta. Sometimes people write this as cis of theta. I don't like that notation. Uh, it's pretty clear, even if you didn't know Euler's formula, that an arbitrary point on the unit circle you can write is cosine theta plus I sine theta, because cosine theta is just x. That's the x component of your point on the unit circle. And y is sine theta. That's the y component, the imaginary component, if you like. But what's remarkable about this formula is you can also write it as e to the I theta. And I'm not going to prove this. The proof involves calculus. And actually, I do prove this in volume 2 in chapter 12, I believe. But I have to give you guys a lot of calculus background first. I mean, you pretty much have to learn a whole course in calculus before you're able to derive Euler's formula. But it is a really amazing formula. And anyway, that's kind of the geometric interpretation of Euler's formula. And anyway, there it is written out. And what else can I say? Yeah, so I mean, I might as well give you guys an example. Oh, yeah, and then there's another really important formula. A lot of people think this is even more remarkable than Euler's formula itself. This is called Euler's identity, um, and or sometimes Euler's equation. What happens when you plug in pi for theta? And as you guys probably know, pi radians is the same as 180 degrees. So maybe I should show you back. That would be the point on the left. That would be the point -1 on the real axis. Because when you go 180 degrees, the real component is -1. That's cosine of 180 degrees. It's -1. And sine of 180 degrees, or sine of pi, is 0. So when you plug in pi radians, you get cosine pi plus I sine pi. But I just said cosine of pi is -1, and sine pi is 0, so that's going to give you -1 plus 0i, or just -1. So you get e to the I pi equals -1. But the way this is usually written is you add 1 to both sides, and you write e to the I pi plus 1 equals 0. And yeah, this is just a special case of Euler's formula. But what makes this particular special case so remarkable? Well, I think there's a lot of things here. First of all, it involves what most mathematicians consider the five most important mathematical constants there are. Um, I'll just start with the integers 0 and 1. I mean, 1 is the basis for all the counting numbers. The natural numbers is the first natural number. People even know about 0 until, well, at least in Europe, they didn't know about 0 until about 1200 AD, when Fibonacci brought it back from the East. It was just 0 was invented in Persia and India shortly after the birth of Christ, I think, or maybe around the 10th birth of Christ. I don't think people know exactly when 0 was invented, but they were using 0 in the Middle East and in India before they were using it in Europe. And 0, as I'm sure you guys all know, is very, very basic to math. As a matter of fact, the reason that the calculus, I think a lot of people think the only reason Archimedes wasn't able to invent calculus was because he didn't have the notion of 0 or infinity. Um, but so yeah, 0 is considered, I guess, after 1, the other important integer constant, mathematical constant. If you like, 0 is the additive identity element of the integers, and 1 is the multiplicative identity element. So anyway, so those are the two most important integers. Also, I guess the two most important rational numbers in mathematics. But then the other three numbers in this equation, e is what's called the base of natural logarithms. At least it used to be called that. Now it's known as Euler's constant. I think I talked about e a little bit already. You really need calculus to really be able to define e, but it's approximately 2.718. It's an irrational number that's a little less than 3, about 2.718. Turns out to be a very useful number. And I'm sure you guys all know about pi. Everybody knows about pi. You learned about pi in grade school. It's the ratio of the circumference to the diameter of any circle. I think most mathematicians still consider pi the most important irrational number in all of math. And I think e is kind of a close second. But there's one more number in this equation, the number we learned about in this chapter, namely I. I is the imaginary unit. And I is not a real number. It's the only number in this equation that's not real. It's imaginary. As a matter of fact, it's the basis for all imaginary numbers. So I think, most mathematicians, I think still to this day, think these five constants, e, I, pi, 1, and 0, are the most important constants in all of math. And they're the only constants that appear in Euler's equation. Pretty amazing. And the only other things that occur in this equation, you have three three binary operators. You have addition, e to the I pi plus 1. So you're adding two numbers in this equation, e to the I pi. Maybe I should break that one down. This actually involves two other mathematical operators, namely multiplication and exponentiation. And I think after addition is the most basic binary operator. But after addition, you have multiplication. And then after multiplication, you have exponentiation. Pretty amazing. So, probably the three most basic binary operators in math also occur in this equation. So, you got the five most important constants, mathematical constants, and the three most important binary operations, all in this one equation. And the only other symbol of this equation is the equality sign, equals. And I don't even know exactly when the equal sign was invented. I think around the beginning of the Renaissance. I don't know. But equals, I'm sure you guys all know, is very important. You got something on the left, something on the right, and you want to balance your equations. You have to have equality. So, nine very, very basic symbols in this equation, and they all make an equation. One of the most important equations in math and a really sophisticated equation. I mean, I haven't derived this equation yet. You need calculus to you need like a whole semester, a whole year of calculus just to be able to derive this formula. But once you have all this amazing math background, you can derive this very, very simple and elegant mathematical equation with nine symbols that holds, and it can prove that it holds. I mean, for a long time, I kind of thought of this. I think I thought of Euler's formula because it's a generalization of this. For a long time, I thought that kind of like a unified field theory of math. And, I mean, the holy grail of physics for, I'd say, the last 100 years or so has been to try to look for a theory of everything, which used to be called a unified field theory. That would be a theory of physics that could, explain everything in principle that could be known about physics with either one equation or a small set of equations. I think there's still a lot of physicists who think string theory may be the theory of everything. I don't think it is. I think it's more like a theory of nothing because it hasn't made any testable predictions, even though the theory is 40 years old. I tried to learn it in the 80s. I don't want to get into this. I had a nervous breakdown after about 3 or 4 years of trying to learn it. It wasn't just the fact that I was trying to learn it and failed. There were other factors too. I don't want to get into that because I don't want to talk too much about my personal life, but it was a rough time for me in my mid 20s. Fortunately, I'm in a much better state of mind now. Uh, but Euler, he's the one who derived these formulas. Euler, by the way, is considered, I think a lot of mathematicians think he was the greatest mathematician of all time. It's kind of hard to rank mathematicians in terms of greatest, but at least he's in the top five. I think a lot of people think it's either Euler or Gauss. I don't know who was greater. A lot of people say Euler. Euler actually did more quantity of work. Euler, it's amazing. Euler, he lived in the 18th century. There wasn't really a lot of math done in the 18th century. I don't know why. Math and science were a little bit of a lull in the 18th century. It was kind of a bad time. There was a lot of corrupt kings and emperors and all that shit going on in Europe. And I think, I think science and intellectual activity I mean, they were still pretty active, but I think they weren't as active as they were at the beginning of the Renaissance. And it seems like things are moving that way right now. I shouldn't get into politics, but I'd say things are starting to move that way here in the United States with Trump, and hopefully they won't continue that way. Whenever you get some totalitarian regime, I think you guys all know that intellectual activity gets suppressed. Happened in Nazi Germany when the Nazis tried to burn all the books of all the intellectuals, and I kind of see a lot of the same things going on now with, we just, got rid of the Department of Education, and there's a lot of ignorance going on now. And, I'm trying to do my part to combat that because I believe in knowledge, and I think knowledge is good. Like they said on the plaque in the Animal House, that was supposed to be a joke, but I actually agree with that. But anyway, enough of that. Enough of my preaching. Anyway, I guess that can. Oh, I want to say one more thing before I get off of this. So remember, I said I wanted to know what 2 to the I was. Well, you can derive it using Euler's formula. And the way you do that is you kind of manipulate this expression. 2 to the I power, you can write that as e to the I to the power natural logarithm of 2. So it's really just e to the I log 2. So if you like log 2, ln 2, that's your theta. So by Euler's formula, that's just cosine of log 2 plus I sine log 2. And you can calculate these things. Pretty easy to do with mathematical software these days, even with pocket calculator. If you do the calculation, you'll find that it's approximately equal to 0.76924 plus 0.63896I. That is the approximate value of 2 to the I power. And it's probably a good thing that my math teacher in high school didn't explain this to me. I mean, maybe I could have asked him in private and he might have been able to do that. But I asked him in class, and I'm sure it wouldn't have been appropriate for the class I was in for him to explain it. But anyway, that's what it is. And that completes my video for today on Euler's formula. So thank you for watching. Long live math. Long live intellectual activity in general. Long live the brain and the mind and what it can do. And I'll see you guys next time. Bye.